Hello everyone and welcome. In today's demo, we'll walk through on how to streamline simulation processes using the latest ANSA, Epilysys, and Meta 2025.1. So join us as we explore the new features and enhancements designed to improve efficiency across the entire simulation process. First of all, in this demo session, we will set up three types of analysis: a static structural, a normal modes, and a frequency response analysis. The pre-processing stage will be carried out in ANSA, where we will demonstrate in detail how the newly introduced workflow simplifies, streamlines, and significantly accelerates the entire model setup process. Once the models have been fully prepared, all three analyses will then be solved using Epilysys as the solver. Following the completion of the solution phase, we will move on to the post-processing in Meta, where the focus will shift towards interpreting and evaluating the results obtained from each of the three types of analyses. Finally, we will wrap up this demo session with a set of key conclusions. To begin with, let us guide you through the model we will be using today. As you can see, it's a car body in white. The geometry is already clean, free of errors, fully meshed, and all connections are set up. The model also contains predefined sets of entities that will be used later on. So having all these in mind, let's jump straight into the model setup process. We will start off with a static structural analysis, a key step in understanding how the structure responds to applied loads. This allows us to ensure that all components remain within safe stress and deformation limits. The expected outputs include displacement, stress, and strain results. This type of analysis is commonly used to evaluate how suspension arms handle forces during cornering or braking, or even assess body stiffness. Ultimately, it's all about making sure the design stays reliable. So, without further ado, let's move on to the model setup. We'll begin in the Structural tab, where we are going to create an RBE2 entity. This will allow us to apply an SPC1 boundary condition later on to the primary node. To do this, navigate to the Structural tab, open the Create drop-down menu, and select RBE2, Many Nodes. Next, select the Secondary Nodes. As you can see, the primary node is generated automatically. Lastly, assign the RBE2 entity to a part accordingly. Moving on, regarding the connectivity, we are able through the same tab. Process-wise, to create an assembly or load case point. It is important to note that these interface entities, as we like to call them, are great for transferring a whole load case once set up to a whole new model by mapping these points. So let's navigate to the Connectivity drop-down menu, Interface Point, A Point, and select on COG to create an assembly point on the center of gravity of each one of these two holes. Select each one of the hole and confirm your selection. Select Apply to apply the assembly points. And since their color turned green, it means they are set up correctly. After applying the assembly points, we will navigate to the Assembly tab in order to create a connector entity to connect those two assembly points automatically. To create the connector entity, navigate to Connector, select from A Point, Auto. Set the proximity to 7, and as you can see, two connector entities are identified automatically, one on the front left side, and another that is symmetric on the front right side. Last but not least, select OK to create the entities. Let's navigate back to the Structural tab and continue with the Load Case setup. For this step, we will use the Load Case Assistant, a powerful tool that helps streamline the entire model setup process. So let's explore its interface. At the top, you can select the solver and the type of load case to set up. In our case, it is a static structural analysis, so we will keep the default options. There are also additional settings available, along with a preview of the load case header that will be generated, as we will see later on. Finally, all related load case entities will appear in the area below once they are set up. Regarding the boundary conditions, we are going to set up an SPC1 entity at the rear part of the body in white. To achieve this, right-click on Boundary Conditions to open the contextual menu and select New Constraint, Single Point. The SPC1 will then be assigned to the primary node of the previously created RBE2 entity. This boundary condition will be named rear left SPC1. And all 6 degrees of freedom will be constrained. In this way, the SPC1 boundary condition is successfully defined. In a similar manner, a force will now be applied to the front left part of the body in white. This is done by right-clicking on Boundary Conditions, selecting New Load, Force, and assigning it to the appropriate assembly point. The load will be named Front Left and defined with a magnitude of 1000 in the negative z direction. Thus, the force boundary condition is successfully established. Although boundary conditions may be defined manually, if they already exist within the model, they can be incorporated directly into the load case assistant. Following the same procedure, we will now add the rear right SPC1, which is a symmetric boundary condition located on the right side of the model. So we right-click on the boundary conditions, add constraint, and add the right SPC1. We will then proceed to add the remaining forces. Specifically, the front right force, which is equal in magnitude and opposite in direction to the previously defined front left force. In addition, 2 further loads will be added, the middle left force and the middle right force, each having a magnitude of 1000 and acting in opposite directions in the middle of the body in white. Confirm your selection, and as you can see, all the required forces and constraints are loaded in the load case assistant. Next, as we talked about in the beginning, we want to output the displacement, strain, and stress for the whole model. So right-click on the Output Requests, New Output Request, and select the displacement. Next, select the strain, and last but not least, the stress. To complete the setup of the load case header, 3 subcases will be created, 1 common subcase and 2 empty ones. The common subcase serves as a container that allows shared entries to be applied automatically to all other subcases, saving the users significant amount of time and effort. For the first empty subcase, only the front left and front right forces will be included. For the second empty subcase, the middle left and middle right forces will be included. Next, by assigning the constraints to the common subcase, they will be applied consistently across both empty subcases. The same way, apply the output request to the common subcase. By selecting Apply, all changes are applied to the load case header. And a preview of the header, generated automatically, is available to be further inspected by the users. Once the load case is set up, the next step, process-wise, is to check the integrity of the model. And for this purpose, we are going to perform some checks and benefit from the pre-made templates. Since this model is going to be solved in Apillisys, a Nastran-based solver, we can take advantage of the dedicated Nastran checks. So navigate to Checks, run Template, Nastran checks, and perform the checks to the whole model. With the model verified, we are now ready to proceed to the solution phase using Apillisys. Apillisys is an integrated Nastran-based solver within ANSA, which provides the flexibility to execute the solution either directly inside ANSA or out of ANSA. Due to its seamless compatibility with both ANSA and Meta, Apillisys effectively eliminates bottlenecks that typically arise when multiple software products are required for pre-processing, solving, and post-processing. In this case, the model will be solved directly in ANSA. It is worth mentioning that by enabling, from the Options tab, Run Meta on Finish, the solver will automatically launch Meta upon completion, allowing immediate post-processing of the results. Having completed the structural load case setup, we are now going to proceed with another load case and more specifically, a normal modes analysis. A modal or normal modes analysis helps us understand the dynamic behavior of the structure. The purpose is to avoid resonance, identify high vibration zones, and provide input for further dynamic or fatigue analysis. From this analysis, we get key outputs like natural frequencies and mode shapes. It's typically used in automotive design for analyzing chassis and body vibrations, as well as components like engine mounts, suspensions, and rotating machinery. So without further ado, let's delve into the model setup. At this point, it is important to mention that this load case is going to be set up in the same file. Once again, the load case assistant will be employed to facilitate the process. We open the load case assistant and select the type of analysis we want to set up. In our case, it is a normal modes analysis. And as you can see, the entries of the load case assistant change, depending on the type of analysis selected. Unlike the structural case, this analysis does not require the definition of boundary conditions. Instead, proceed with defining the displacements for the whole model as output request. The next step required is to define the modes that are going to be extracted in the frequency range of interest. To do that, right-click to Modes Definition, select New Method, and set the V2 parameter to 50 Hz. This means that our frequency range is below 50 Hz. Next, define an empty subcase and apply all entries to the subcase. And the last step before setting up our load case is to access the Options tab that contains all commonly used parameters, ready to be fine-tuned for solving. To accelerate the computation, the Automated Multi-Level Substructuring or AMLS parameter will be enabled. Apply the changes and press OK to confirm your selection. Last but not least, right-click on the header to mark it as current. Now our model is ready to be solved. It is worth noting that in this case, epileusis is once again utilized. Having seen all of that, we are now ready to proceed to the last but not least type of analysis we're going to investigate, the frequency response analysis. A frequency response analysis helps us predict how the structure reacts to dynamic loads over a range of frequencies. The primary outputs include the acceleration versus frequency curves and the dynamic stresses. This type of analysis is commonly used for evaluating road vibrations, rotating machinery vibrations, as well as random ones, and in general, assessing NVH performance. Navigating back to ANSA and from the load case assistant, we will select the type of load case we want to set up. In our case, it is a modal frequency response. In order to set up this load case, the definition of a frequency load as boundary condition is required. So right-click on the boundary conditions, select New Load, NVH frequency. The frequency load is going to be defined on a set of assembly points. Select the set of assembly points under the name NVH frac set and inspect them accordingly. Next, set the degree of freedom to 3, indicating the z direction the force will be applied to. And the amplitude is defined using a tabled 1 entity, indicating the magnitude of the force that will be applied to the assembly points. Here, you can see how the tabled 1 entity is defined. At this point, it is worth mentioning that many other options exist regarding the application of the frequency load, such as the definition of the phase or time delay. Once you complete the setup of the load, select OK to confirm your selection. After setting up the boundary conditions, the next step is to define the output requests. As mentioned earlier, we will specify the accelerations for the set of assembly points. This will allow us to extract acceleration frequency curves for the assembly points of interest during the post-processing. Select OK to confirm your selection. Moving on, we are going to set up a frequency range. This is the range of input excitation frequencies defined in Hertz, used to calculate how the structure reacts under harmonic loading. So, right-click on the frequency range, New Frequency Range. Frequency range. We will define the range using a FREQ1 entity, the most commonly used one. Set the first frequency in set to 1 with a frequency increment of 1 and the number of frequency increments to 49. Insert the FREQ1 entity, select it, and confirm your selection pressing OK. Under the defined frequency range, we are going to define the modes. Right-click on the Modes Definition, New Method. Set the V2 parameter to 100 Hz and confirm your selection, pressing OK. The next step is to navigate to Options, to the Damping tab, and set the structural damping to 0.02. Enable once again the AMLS parameters to accelerate the solving process and press OK to confirm your selection. Assign all the entries to an empty subcase. Select Apply to apply the changes to the load case header and press OK to confirm your selection. Last but not least, mark the load case header as current. And once again, the model is ready to be solved with Apillisys. After completing the solution in Apillisys, it is now time to move on to the post-processing stage in Meta. Here, we will examine each load case in detail, starting with the static structural analysis. As you can see, we loaded the model in Meta. To read the results, navigate to the Results tab and read the displacements and the von Mises stresses by selecting Read. Enable the fringe to visualize the results and inspect your model accordingly. In order to visualize the element presenting the maximum stresses, it is possible to create an annotation. To create an annotation, navigate to the Insert tab, select the option on Min-Max. Alum Scalar Max, von Mises stresses. This way, an annotation is created. Select Follow in order for the annotation to follow the model and to enhance its visibility. After completing all post-processing actions, the next step is to save the work as a project file. To do this, navigate to File, Save, Project. If you choose to save references to results files instead of the actual data, the project will store links to the results, making it possible to overlay the current project on another model. This means all post-processing actions can be reapplied with a single click. Specify the name Static, indicating the static structural analysis, and save the project. In order to overlay a project, go to File, Overlay, Overlay Project File. Specify the number of overlay runs. This number indicates to how many files the post-processing actions will be applied. In our case, it is only one. Select OK to confirm your selection. Notice that the old file appears on the left. Then, choose a new file to overlay, for example, the static 2000 load case, which has the same setup but with the applied forces doubled, 2000 instead of 1000. Click OK to confirm your selection, and as you can see, the same post-processing actions are automatically applied to this model as well. This functionality significantly reduces time and effort, as it eliminates the need to repeat post-processing actions manually, streamlining the workflow into just one click. Having seen how we can create annotations, save project files, and overlay them, we can now move on to inspecting the results of the second type of analysis we previously set up, the normal modes analysis. To begin, navigate to Results, Deformation tab. In the Read options, set the scale factor to auto-calculate, per each state. This ensures that the scale factor is automatically adjusted for each mode, making the visualization more clear. Select Read to read the results. Next, enable the fringe and, from the drop-down menu, select T-Deform so that the displacements are properly visualized. Now let's examine the results. As expected, the first 6 modes appear as rigid body modes, confirming that there are no unconnected parts in the model. We can also identify a torsional mode at approximately 32 Hz, which is not favorable for the car's design. However, thanks to the overlaying capabilities we demonstrated earlier, it is always possible to make corrections in ANSA and post-process the new results in no time. Having examined the results of normal modes analysis and identified the rigid body and torsional modes, we can now proceed to the final type of analysis, the frequency response one. This post-processing step directly builds upon the modal results, since the natural frequencies and mode shapes we just inspected define how the structure will respond when subjected to dynamic loads over a range of frequencies. Let's begin by extracting some acceleration versus frequency plots. Navigate to the Curves tab and select Scan. Next, navigate to the Results tab. We only want to extract the accelerations versus frequency curves for the set of assembly points the frequency load was applied to. For this purpose, we're going to enable the column filter, which allows us to filter assembly points by name. By typing NVH in the filter, all relevant assembly points are displayed. Select all of them and choose to plot the results in the translational Z direction, since this corresponds to the direction of the applied load. Leave the default option, New Window, and then select Read. A new window will now be invoked, displaying the translational accelerations in the Z direction versus frequency curves. For the selected assembly points, enabling us to clearly evaluate the dynamic response of the structure across the frequency range. Let's now inspect the plot. First, it is important to adjust the y-axis to a logarithmic scale. To do this, right-click on the axis, go to Options, Range Type and Steps, and set the type to log. Next, in order to better inspect the frequencies and the peaks that appear, adjust the x-axis increment. Double-click on the axis, navigate again to Range Type and Steps, and set the increment to 4. Finally, box select the peaks you are interested in and focus on the values of your preference. This approach allows us to identify the most critical frequency ranges, ensuring that potential resonance issues can be detected and evaluated early in the process. Having seen the last type of analysis and reviewed the results, we can now wrap up this demo session with a short recap of what we have seen. First of all, in this demo session, we showcase the most powerful capabilities of ANSA, Apillisys, and Meta 2025.1 that offer an intuitive workflow from mesh to results, enabling us to set up multiple types of analysis in no time, boosting this way our productivity and reliability. That concludes our demo session. Thank you for watching.